actually asked to evaluate the definite integral for this function from 2 to 6 using the definition of integral. And I'm assuming that means the limit as n approaches infinity of f of x dx, the sum as from I equals 0 or 1 to n, depending on whether you use left-hand endpoints or right-hand endpoints. In other words, we're going to take this blue region and start dividing it into, if we use left-hand endpoints, this would be the first rectangle. This would be the second rectangle, and so on. And we'll let the number of rectangles approach infinity. We have to decide what a formula is for each of these this could be x sub 0, x sub 1, x sub 2, all the way out to x sub I. So here we go. Here's the function. If we're going from 2 to 6, that's 6 minus 2 over n. This would be delta x, the width of each rectangle. And to get the x sub 0s that are, or the x sub i's that are going to give us the height of each rectangle, you could picture starting with x sub 0 is at the left-hand endpoint, and we add on 0 widths, 0 of these 4 over n's. If we want to find the value of x sub 1, which would be starting at 2 and adding on 2 of these 4 over n's, one of these 4 over n's, we'd start with 2 and add on 1 of these 4 over n's, and so on. And so we see a pattern. To get to the ith x sub I, start at 2 and add on I of these 4 over n's. So there's a formula for x sub I. And so here's the definition. Limit of a Riemann sum. So here we are. Here's the function f of x. And I've plugged in a formula for x sub I wherever there's an x. So this expression right here is a formula for the area of the ith rectangle. Okay, and I started at 0 because I'm using left-hand endpoints. And I won't go through all the algebra. This is all algebra down to here. Squared this binomial, distributed the -4, distributed this 4 over n. After simplification, this is what we got to. And now we're going to use summation properties to evaluate this as n approaches infinity. So I can take the sum from I equals 0 to n of each of these individual terms. And while I'm at it, since n is just a constant, I can move the constant out front of the summation symbol. So here's the work. Here's the first term. I move the 12 over n out in front of the summation symbol. That just leaves a 1 inside the summation symbol. For the second term, 128 over n squared moves out front. Sum from I equals 0 to n of I squared, and so on. Now, how do I evaluate each of these summation symbols that I've underlined in red here? Well, here's the formulas. Sum from I equals 1 to n is this. And for I squared, it's this. Now, if I start at 0, that's not going to change the formula, because if I put 0 in for I still get a 0. So if we go back to this board, I do have to use n plus 1 for this summation, because I'm adding 1 plus 1 plus 1 plus 1, n plus 1 times. I'm not going from 1 to n, I'm going from 0 to n. So this is n plus 1. Here's the formulas. If I distribute this 12 over n times each term here, I get this. If I rewrite 128 over 2 as 64 and put n over n times n plus 1 over n squared, I get this. Here I haven't done the division yet, 192 over 6. If I multiply these binomials all together, I'll get 2n cubed plus, I don't really care what the rest of it is, because if I divide them by n cubed, those are going to approach 0. So this limit is 12 as n approaches 0. This is 0. This is 1, because the rational function has the same degree in the numerator as the denominator. So you could picture a plus 1 here if you wanted to. And 6 into 192 is 32 times this limit is 2, coefficient of the n cubes. Gives us 140, and that's what we got from Desmos by evaluating the definite integral using the fundamental theorem of calculus. So 140 is your answer. Pause the video and take some notes so you can see the steps involved here. There you go. Hope that helped. If you have any questions, post a comment.